when we are looking at nanoscale fabrication, there are two ways. We either come top down or we go bottom up. So in this, uh, to make devices, we do a lot of work which is top down through lithography. When we are synthesizing small objects, nanomaterials, we do bottom up, where we have well-defined kind of molecular reactions that we know, and we design them to get to the desired outcomes. So in the top-down lithography, in the top-down fabrication lithography, and especially next generation lithography has enabled how we do things. And if you think about it, next generation lithography, some of it has already become commercialized, where is being used in commercial fabrication. Some of it is that has been uh, done in research labs. Some of those things have become into products. Some of those things have stayed intellectual curiosity. But there's continuous effort going on to in this domain, what we call next generation lithography. So we talked about numbers, we talked about dealing with wavelengths, we talked about dealing with the numerical aperture, and there were three important factors that we are interested in: minimum feature size, depth of focus, and pitch. How often can we make things next to each other? And within lithography, there have been some techniques that have been done, like what you call optical proximity correction. So the upper figure shows that if there is a feature, like a very small feature, like an L-shaped thing or a square, because of diffraction limitations, when the light projects, the edges don't come too sharp. So there have been some physical interventions that have been done, like if you look at the mask size, mask design on the lower picture, you see they have added some extra increased edges, like here you see, or here. So when the light is projected, it gives us very sharp features like which is shown here, instead of becoming rounding off. So this is an issue when we are going down, reaching the diffraction limit, right? Waves, they construct, they interfere with each other. So these are physical ways where we have been adding, calculating what compensation we need to do. We add into the feature, and hence, after all said and done, after all the interactions of light, we end up having good feature translation. Professor Mark Madhu, he's a professor at UC Irvine. Interestingly, my PhD advisor took a couple of courses from him also. I met him, very fantastic gentleman. Uh, so some of the slides are taken exactly from his lecture. So that's a disclaimer. So I owe out of it to some big people. Another physical thing that they have done to extend optical lithography is to what we call using phase shift masks. I know some material we have already seen, so I got better slides, and I wanted to touch upon a little bit more to see that we tried to push optical lithography for a long time with many different innovations, but we still hit a dead end where we couldn't make things smaller. So hence we will talk about next generation. So in phase shift mask, so we know the mask has these opaque regions and transparent regions through which light goes. So, but light is a wave, right? Wave travels in phase, some angle. If you take two waves and make them out of phase, this is essentially, you're not changing the intensity, you're not changing the wavelength or frequency of the light. So light stays the same. The only thing is two waves go out of phase. Now, if one wave is at high, I should do it like this in front of the, If one wave is at the high, the other wave would be at the lowest end. So when two waves which are destructively interfering each other, they would cancel out the signal. So hence you would get a sharp edge, right? Like it is shown here on the right hand side, that you get a sharp edge between two features. So hence the light would result into exposure of the photoresist material with a very sharp feature. So far with me, I know it's lots of visualization, and I'm I'm hoping that I can help you see, visualize what's happening here. So those phase shift masks basically change the phase of light from one opening on a mask than the next opening. So hence, those two features can be translated much more effectively, right? So there's lots of companies who you can make the basic mask, the VLS engineer, and then you can give it to those companies, and they can improve on it and optimize it and do those OPZ and PSM things and give you better mask. So this was the push, in addition to pushing the wavelength down to get smaller and smaller. But then we hit a dead end, right? But
excuse me, Doctor.
Yeah.
Can you give me 1 second, please? Can I step up just to check something?
Yeah, go ahead. You want us to wait for you?
No, that's fine. I'll be back in a bit.
Oh yeah.
Thank you.
During the lecture, if you have to, like, for a few seconds, a minute, go here and there, that's perfectly fine. I don't like if somebody just leaves it, like I cannot see two students. I will not name them. You know, you can see them. I cannot see them at all. They haven't turned on their computer at the video at all. I know one student, Julio. I think he's not in his regular desk position. Amara, where are you? I don't see you. All right, so now we get into what you call next generation lithography. So the idea is still the same. You have to transfer the pattern, right? But now instead of using light or UV or variations of UV, we have to go somewhere else. We take extreme UV. Now when you say extreme UV, we are talking about X-rays. X-rays are not light, right? It is a wave, but it is very high energy radiation. We all have got X-rays done in our lives, right? What do you know about X-rays? Tell me something about X-rays. What do you remember about X-rays?
I can't remember if they were beta or gamma. Which one? No.
Just tell me one fact. Like, as a regular person, you went and I got X-ray done. One fact that you remember from that activity.
Radiation.
It's very probably dangerous radiation, because I remember technician goes away, right? Technician doesn't want to be in that room. What else do you remember? One fact, another fact.
The lead vest that they put on you.
They put on you a vest on you, right? So maybe to cover other parts that they don't want to be exposed. What else do you remember? The radiations just go through our body, right? And they hit they have a detector on the other side. What else do you remember from the film, maybe X-ray film that we get? So it can go through flesh, but bones, it has, not all of it goes through. So hence we get some feature of the bones transmitted, right? So the transmission through bone, transmission through tissue is different, right? Different medium. What else do we remember from X-rays? They put metal numbers maybe on the, they may give you a vest with metal numbers on it. So metal numbers can get transferred on the sheet itself. Different places, there are different ways. How do we do that? What else? Have you ever looked at the X-ray source? It's a big equipment, right? It's an X-ray gun, basically. So you need a a big source in which we have X-ray gun in which the rays are created.
Now they have it even in like a smaller gun. I was just remembering that for the teeth. Like for example, if they need to get specific
Right.
pictures of the images of the teeth.
Right. Now, think about tooth. They are the strongest material. It goes through that also. It's opaque through visible light, goes through that. So now, high energy means it requires lots of, you cannot use glass for optics. So you cannot use glass, especially to send the radiation through that, because it's going to just ignore it. It's just going to transmit through. It's not going to, an optical material is supposed to change the direction of the rays, right? That's how we can focus things on. But X-rays just pass through. So that's another problem. You need to have special kind of optics. You need to create different kind of masks because it can go through virtually everything. So this is where extreme UV or proximal X-ray lithography, PXL, as they have tried X-rays, but because of the cost associated, because of the difficulty in handling the radiation, that probably has not been pursued. But what has been pursued, this is, we're talking about the first two bullet points, because I'm going to start more details on the third bullet point, because that's what has been ultimately industry has used and doing right now. Right? Electron beam, not maybe for production, but for assessment, for investigation, or to make devices. And we'll see the problem with them, why we cannot do them for industrial application. What are the challenges? But electron beam is then the idea that instead of using light and flooding, just take an electron beam and start writing. Have you played with laser and cat? Where's your cat at there? Right? So you have played with lasers. You all know lasers, right? So laser is a very pointed, sharp ray. Very, the bunch of rays, but very sharp, pointed kind of a transmission of radiation, light. And E-beam would be the same, except electrons are too small. If they were, if you throw them in, if you try to focus them, that too small spot in air, there'll be too many diffractions. So we have to have a specialized equipment where we create vacuum, we pump everything out, and then we have a bunch of lenses. But in this case, the lenses would be electromagnetic coils to bring the thing very narrow, and then use it to write the feature or whatever device VLSI design we want to write. So that's what we do with electron beam. Let's get started and we'll look at all the others as we build upon it. All right, so electrons, they interact with matter more strongly than X-rays. And essentially when an electron strikes a matter, it has 2-3 reactions that happen. Electron would strike, and because we have the law of conservation momentum, law of conservation of energy, it's going to give its energy to other electrons, right? To other particles. Some of those bombarding electrons are going to reflect back, and it's going to make some other electrons to come out and cause a cascade of reactions. So this is essentially the feature that we use to coat an E-beam lithography, an E-beam resist, same like you're using a UV resist, right? A photo resist, what we call a coating of material. So we coat a material that can undergo changes because of electron exposure. So we use electron beam. Let me show you. So here's the right-hand side shows, just look at the column. So this is where the electron gun is. We get electrons coming out of it. We need to speed them up so we can use coils again. So these, what you see as a plate here, these plates are basically bunch of electromagnetic coils, right? So with which you can change the path of electrons, their charged particles, right? So electrons travel, keep on traveling. We have again bunch of plates, and we want to point those, all the electrons coming out into very sharp point, like a laser. Laser is too big for that, even compared to the beam that we get. So we have this tightly focused spot of electrons, and we start writing with those electrons on the surface. The surface is coated with the polymer material, what we call as E-beam resist. It's a material which undergoes chemical changes when it is exposed to electrons. So we directly write our pattern or whatever device design we want to write. Can somebody tell me what's the problem with this process? You can write electronic scale things, very small things. What is the challenge with this process? Somebody tell me what is the challenge with this process? When you have to think about it, if you think about the optical lithography, that was like you make a stencil and you put that stencil on a wall and you just paint it, right? It was like that.
So
Almost.
it would be less accurate to do.
No, it's more accurate, but the problem is the example I was giving is that, think about it, if you have a wall and you make a stencil, right? You know, stencil, and you can just paint it, and you take the stencil, whatever your design you had on stencil is printed on the wall, right? But instead of that, now you have to write that whole feature with hand, whatever is there. Which one is faster? You guys know what's a stencil?
Yeah, the stencil would be quicker. Just to,
Stencil will be quicker, right?
yeah.
Instead of writing the whole feature one by one. So this is, the concept is called throughput. So with
Right.
E-beam lithography, we can write very, very small, very, very accurate, but it is a slow process. So if I own the company, I want to quickly make devices more and more quickly, but E-beam is a slow process.
Okay.
Makes sense? So that's becomes an issue. So here's the example that if we have to make 15 points, 15 circles, you have to go at each space and use your E-beam to write that circle, then switch off, go to next place, write your circle, write your circle. Right? Instead of that, if we were doing UV lithography, I would just make a mask with 15 circle and just flash the light once. Everything will be, but the problem is size. I cannot make smaller things with UV, right? So that's the issue. Now, here it says scanning device is just like an SEM. We haven't talked about SEM, that's coming. SEM is scanning electron microscope. It's the same process that we use in an electron microscope, but here what we do is we have 4 extra capabilities, which is there where we can turn the electron beam on and off. We can put dots next to each other, pixelation, and we can very accurately place where we want to go. And we can blur the E-beam also, right? So just by defocusing, we can blur it, make bigger patterns as well. Now, E-beam lithography has evolved over years also. Just by, instead of just writing one point, we have gone through lots of variations where we are now, these are 2, 3 types, scalpel and prevail. The idea is that we can put more pixels in one shot now over years. So we can, instead of writing just one line, we have done some techniques where we can write many lines now. And we'll look at scalpel at least for one. Instead of using one beam, we are using a defocused beam and covering and using a stencil kind of thing to still expose a bigger area with E-beam lithography. Now, these are examples of some real examples of E-beam lithography where we have made nano electrodes to detect molecules, for example. This lower right-hand side, these pictures here, I took these pictures. I made these devices myself. So, and that was a long time ago. What's the date on these? 2006. Yeah, this is 2006. And this here, the thing is, this is gold. This is gold. So there are two electrodes of gold coming, and then there is a break in between, and that's the sensing part. You see my arrows? So this middle one, where I'm putting a thicker arrow, that's the sensing part where if you get some very small molecules, think about it, toxic agents or virus. So you can get one virus to sit there and you can see the conductivity change through the electrodes. And we can detect single virus level kind of thing. The distance between those two electrodes is 10 to 15 nanometers. This is really, really small that we fabricated a long time ago. We did some DNA detection work with that. E-beam lithography. So these electrodes were made by E-beam lithography, but the process was slow, right? These are the disadvantages of this process. It's a serial writing process, gives you low throughput. It's expensive because you have to spend so much time. The defects are at atomic scale also. So if something doesn't stick, you wouldn't know unless you go to the later steps. Alignment, going from one layer to making another layer, then you have to align them. Remember, we had multiple masks. That becomes an issue. But the advantages are very clear. You can make really, really small features. You can make variety of designs because you are basically writing a design, right? You are, think about it, it's not a stencil, it's artwork. In artists, they don't use stencil, they use whatever, brush strokes or what. So this is like that. You can have flexibility and you can write the design on many different kind of substrates, silicon, glass, whatever, silicon nitride, many kind of substrate can be used here. Questions? Now, if you understand electron beam lithography, the next one is ion beam lithography. Same principle, the only difference is instead of using electrons, we are using ions. What is an ion?
I'm maybe remembering incorrectly, but isn't it just different than normal charged atom?
It's just charged atom. Edgar, it is just an atom that's charged, right? Because you have taken one electron out or maybe given an extra electron, right? Positive ion, negative ion. Now, we were talking about electron beam lithography, and now we're talking ion beam lithography. What can you say about the size of the particle? Difference between the size of the particles.
Ion would be bigger than electron, wouldn't it?
Ion would be much, 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 much bigger than electron, right? Exactly. Now, if I ask you guys, and let somebody else answer this, if you have a bigger thing coming at you than a smaller thing, which one will have more energy to transfer? So you have, I don't know what's a good example. You have, I don't know, a car coming to you and a truck coming to you. Which one has more energy to transfer? I'm not saying it's going to hit you. I'm just saying which one has more energy to transfer.
I
Yeah.
know from experience.
All right. Let's ask Amara. Amara, you are a basketballer, right? So two balls hitting at the same velocity, basketball and I don't know, tennis ball. Which one has more energy? A bigger ball, bigger mass, or a smaller mass? Which one has more energy? Which one will hit you harder?
The basketball,
Basketball, why is that?
because this has more surface area.
It is more mass.
Yeah.
It's mass. And mass, it has more momentum. It's the momentum we are looking at. What is momentum? You guys remember what was momentum from your high school physics? Amara, we couldn't hear you. What's up with your microphone? How do you define momentum?
Is density times mass or density divided by mass? I forgot.
All right. Now is the question. Cecilia, what is momentum? Rachel, wait, did I say it right? Rachel?
Yes, that's my
What momentum?
like in definition or
Yeah, simple definition. What's momentum?
motion that an object has, like
Motion, yeah, it is. It depends on motion, but what's the equation? It's a simple equation.
I can't think of it off the top of my head.
It's mass
Product
versus.
of mass and velocity.
Yeah, Cecilia got it. Mass times velocity. It's as simple as that. Now, mass times velocity is mv. That's it. Okay.
Professor, also Amara is saying that her mic is not working properly on chat.
I saw the chat message. Yeah. So now you have a bigger particle, but you cannot write as small as you can write with electron, right? But you can transfer more energy. So it's same principle, but you have probably more variety of things that we can write because we can change the ion source. You can use one type of ion versus another type of ion. Of course, there are limited number of ions that we can use as in what it says, ion source or ion gun. So those energetic ions, they come with more energy than they would come with, than the electrons would come with the energy, right? So more energy means we can use very thin resist. They don't have to go all the way in the resist when they hit. And you have variety of having heavy ions or light ions. So light ions, the benefit is that they would travel deeper. So which means they can have, you can uh, have a thicker photoresist to cover much. If there are heights and lows on the wafer, so you can cover with a thicker resist. But the other problem is the light ions would start causing a bigger reaction. So which means this is what it shows, a bulge type of thing. So they would start causing, so your feature size will become bigger than what you want it to be. On the other side, if you have a heavy ion, they would stop much quickly. But now they're heavy, they're bigger. So they also, it's a problem of how small can you make things with that. So another thing what we do with ion beam, and it's very common now, we use ion beams to machine at nanoscale, machining, machining. We make big things. When you do machining, you make, I don't know, rotor or whatever you want to use in bigger things. We may make 3D printing we do. So that's also kind of instead of cutting things down, we are building bottom up. So that's another concept of machining. So gallium ions are example of FIB. Many things they use gallium ions to do the, we call it FIB, focused ion beam. We just call it FIB. We have used FIB, and it was a paper I think we published 2 years ago. Here we use FIB to make 2 nanometer holes into silicon wafer, where we could then detect single virus in that small hole. So you can make holes so small, which can be used to detect biological entities directly. Here's an example of using ion beam to make these nanopores. So this is an old paper. I know this lady, Jalili, Arkansas. So what you are seeing here is it's a very, very small, even smaller than what I'm making. This is the size of the nanopore hole they made in a thick wafer, about 2 nanometers. So they could detect single DNA molecule using that kind of thing. So bio-nano, we are getting a little bit in bio. At the end of this module, we'll be looking at bio-nano interface as well. So this is an example of an ion beam machine where they are throwing ions. The ions are coming out of ion gun, and we are making them with these 2 plates you see. These are used to deflect them. So again, electrostatically, you can move them and make a very narrow beam coming out of that machine, and then you can use to write on the surface. All right, let's get going. So we could write with single beam, and then now we are getting into where we say, okay, we can create a mask and we can flood the mask, and that can give us the image also on the surface of a wafer, right? So there are 3 examples given here that where you can write directly, or you can use a stencil, or you can use a projection system where you demagnify, you make something and then you make it larger, and that can result into giving you a feature on the surface. And this is what I was saying, scalpel. So instead of using one electron beam, what they came up with name scattering with angular limitation and projection electron beam lithography, a big name. But the idea is that instead of using one beam to write, they again through a diffused beam, a bigger beam, and then you use kind of a mask which has some parts where it would stop the beam from going through and some part where it will let the beam go through. And once you get to the surface, it is shown on the right hand side, you would get that image transferred on the surface of the wafer. This is the wafer, this is the mask, and electrons are coming from this side, right? So they have made 50 nanometer features on silicon nanomembrane. Here, this is the silicon nitride membrane, right? So the example of electron beam, but using a mask instead of writing directly. Why are we doing this? Again, we can write small, but our goal is to increase throughput. Remember the graph we saw last time? We want to make things smaller, but we want to make them fast enough, right? So it stays economically viable. So the way we are doing electron projection lithography, so you see the word, we are, instead of using electron beam lithography, now we say electron projection lithography. So instead of using one beam, we are projecting bigger beam and using a mask with it. Are you with me on this idea? Thumbs up, down? All right, very good. So similar way, they have come up with ion projection lithography. So instead of using one ion beam, again, they make a stencil. So when I say stencil, stencil is a same thing that we know for screen printing, like they put on shirts or on the wall. We don't see that now too much. It used to be. They show it, still shows in movies that they put some signs on the wall, secret signs on the wall through stencil. So it's the same concept. Stencil project a big beam of ions, and here it says the masks are silicon membranes. So they're using hard material as a mask, and then they transmit the beam through, and that results into on what you call the exposure on the surface and changes the resist properties. All right, so this was more on where you would use light or similar concept like light, but instead of light, we are using electrons or ions. Then there is this concept, what we call scanning probe lithography. This is again something related to AFM or atomic force microscope, which we have another micro lecture on that posted. What is scanning probe? So a probe word in this context is used to define a very sharp tip made, and the tip is then scanned on the surface of the wafer. The tip is so sharp that the edge is the what you call the edge is few nanometers. So we use that to write directly on the surface. So we are physically writing, but that writing here can be done in a number of ways. Like we can chemically put some chemical down on the surface using that thing. So we are using it like a pen in that case, right? So ink and transferring the ink, basically chemical material. We can mechanically scratch the surface. We can use that tip to heat a surface at very localized point. Or we can apply a voltage from that tip also on the surface. Or we can use that to manipulate nano structures on the surface. There are all different ways how this word scanning probe lithography can be done. So two important concepts: scanning probe. Probe is a very sharp tip. Tip is like a needle, right? But we call it tip because from the backside, it's like on a. If you think about a jumping, the diving board on a swimming pool, right? You have seen diving board on a swimming pool. So if that's a projected thing and you put a very sharp tip at the bottom, and that tip is what you would use to write. That's the concept of scanning probe. AFM, atomic force microscopy, is a type of a scanning probe equipment. It's a type of a scanning probe equipment. What it does is we use atomic force microscope to write on the surface. So here, few examples are given where they have maybe they dip in some chemical solution and then use that tip to place those specific places. So Northwestern University, there's some groups from NU who have done lots of work on that. There's and they continue. They have spun off some companies from this work as well. So these are few examples where they are using, they're adding the material on the surface or removing the material with the tip. And that gives us a very small feature on the surface. So these are nanometer scale features they have written. You have very, very high resolution, very, very small objects. What's the problem? What's the problem? It's the same problem what we knew about E-beam lithography. What is the challenge with scanning probe lithography?
Too slow because of
So,
essentially,
yeah, throughput. Throughput, how fast can we make things? That's the problem here as well. So they have done interesting things of getting over the throughput problem. This is now just a cartoon going much closer on what happens. So you can take a sharp tip and tip, there are different words. It can be the edge of the needle. You can call it a nib. Nib was another word they used to define the edge of a pen, for example, right? So now what they're doing is they dip it and then they move. So in this cartoon, what they're showing is that these are molecules which have this green and pink subunits in it. So the pink unit is hydrophobic, doesn't like water. So when you put it down and if there is water, the pink will go away, try to stay away from the water. So whole molecule will kind of align itself. There's a YouTube lecture, very important YouTube lecture I have posted from Professor Ron Reifenberg. I've taken a course from him from Purdue. He has a very, very nice lecture that I posted on scanning probe lithography, right? Make sure to go through that. All right, so this is now a type of scanning probe lithography. It's called dip pen lithography. They called it dip pen nanolithography, DPN. So if you Google, you'll find DPN is this concept using small tips to transfer different molecules in a very precise way. There are many variations they have come through showing how this is done. So they have made holes in next to the tip. They have made double layers tips so the molecules, so your ink can keep on flowing continuously. And they have shown things with many, many different things. Again, throughput. Throughput is the challenge. Here's an example of features written by researchers at Lawrence Livermore National Lab. Again, you can see nanoscale features and nanoscale designs have been made. So you look at these, you'll find these are really key papers. These are the papers who have started this area. One way to overcome that, they have made parallel dip pen nanolithography also, where they have created many, many, many tips, and they take them and they stamp them to write things, right? So on AFM, again, the list that I was talking about with the voltage, with oxidation, with the many different features they have applied to transfer pattern at that using this very sharp tips. Here are some more examples of AFM lithography where they have used to write these are called high aspect ratio features, which is a big challenge. You can make things small, but how can you achieve height when you make those things? These things become interesting when you are talking about MEMS devices, micro electromechanical systems as well. So with AFM lithography or scanning probe lithography, they have easily achieved less than 100 nanometer kind of features with those. And there's another variation, what they call nano stencil, where they have put, if you look at this thing, this was what the concept which I was saying, that it's kind of the jumping board and there's a tip at the bottom. In that tip, they have created holes so they can detect not just the position, but they can shine through light through those precise openings on that tip. So this is done in Switzerland, where they used these small holes to expose the resist at the bottom or to deposit material through those holes in those very precise ways at the surface. So when you say deposit, so they are basically using, again, a vacuum chamber and using a source of metal vapors, and they use that to deposit it at nanoscale. So here's an example of a copper nano ring where they made a ring which is just 200 nanometer width of the line that has been made. There is an example of copper nanowire with just 4 nanometer height. So this is again made with scanning probe lithography. Now, what do we want? Where do we want to get there? We want to write massive parallel writing. It's like your hard drive, right? Your hard drive has one head. So it's reading one place. Can we make massive parallel heads so it can be probably reading multiple places at any given time? It's a similar concept, but they've used those to precisely take, but not in parallel way, but one probe to place atoms at different locations. So this, the word IBM that you see, this is a real picture of these many atoms that have been placed in those position or those location. Actually, they have changed the surface by placing atoms on those surfaces, single atoms. All right, so let's look at one more nano imprint, or what do you call next generation lithography, called soft lithography. The idea is that we call it soft because we are using polymers, molten polymers. So you make a kind of a stamp, just like they use stamp in I don't know, post office, or I don't know, where do we see stamps? These are stamps where they put it on the ink and they put it on the paper. So similar concept, that we make a stamp, you pour the metal on, pour the liquid on it, polymer liquid, and when it cures, when it hardens, you take it away and use that as a stamp to transfer patterns. So here the blue thing is now the stamp. You dip it in this red ink and you use that to transfer the pattern on a surface. So just a simple idea of using it as a stamp. Instead of using light or instead of using scratches, you take the idea of stamping the design on a surface. So this stamping concept is another thing, what you call nano imprint lithography. So instead of using just an ink, what they are doing is they are using a coating of hard material and they press it down. They press it down with high pressure and high temperature, and they transfer the design into some polymer material. All right, questions? All right, so another example of what you call nano imprinting. This is what I was saying. So they have a layer of material, they press this green thing hard, and they transfer the pattern on that hard surface. So these are examples of nano imprinted wafers. We have done some work with nano imprinting as well. All right, so here we'll stop just to give a comparison that there are single in scanning away, there is a parallel way how you can do that, but the goal is we are trying to play with high throughput. We want to get high throughput, we want to make smaller feature size. That's the end goal. All right, so let's stop here.